2.3, continuity. Your objective is to identify the intervals upon which a given function is continuous and understand the meaning of continuous functions. Remove removable continuities by extending or modifying a function and apply the intermediate value theorem and the properties of algebraic combinations and composites of continuous functions. Okay, so first of all, continuity at a point. Any function y equals f of x whose graph can be sketched in one continuous motion without lifting the pencil is an example of a continuous function. That is straight out an algebra definition of continuity. As long as you can draw without picking up the pencil, it is continuous. If you draw it and then stop, then they're no longer continuous. So on this one, find the points at which the given function is continuous and the points at which it is discontinuous. So we're going to start with continuous. So on this one, this means that the ends must have closed circle, a bracket. So this one here, this line comes down. We don't know if it goes to 1/2 or if it goes down to 0. It looks to me like 1/2. So we're going to go 1/2 to 2. But 2 is an open circle, so we're going to keep it open. Then it starts continuous again at x equals 3 off to 6. Those are all the points. It is not continuous at 2, but I do want to point out that it is continuous down here because it's an endpoint. So not continuous. Once you have one, it's just to fill in the blanks for the other. So negative infinity to 1/2, open circle, union that, and then it starts again at 2. 2 ends at 3, open circle, union that, starts again at 6, and since there's nothing behind it, it continues on to infinity. So we're really, as we work through calculus, are going to be more concerned with our continuous functions than with our not continuous functions. Okay, so on this one here, find the points at which the function f of x equals 2x plus 3 is continuous and the points at which it is discontinuous. So this is just a domain idea. So I take 2x plus 3 must be greater than or equal to 0. Solve for x. So 2x must be greater than or equal to negative 3. X must be greater than or equal to negative 3/2. So in interval notation, negative 3 over 2 to infinity. Anything prior to that, so this is the continuous part, anything prior to that is going to be not continuous, because this guy goes off to infinity. So not continuous is going to be negative infinity to negative 3/2. But in all reality, this is where it's not, the domain is not defined. So it's not that it's not a continuous function, it's a continuous function in its domain. Okay, continuity at a point. Interior point, a function y equals f of x is continuous at an interior point C of its domain if the limit as x approaches C of f of x equals f of C. So if I had x squared plus 3 and I was doing the limit as x approached 1. Well, if I plug in 1, I'm going to get 4. But guess what? F of 1 is equal to 4. My limit equals 4, my function equals 4, therefore it's continuous there. A function y equals f of x is continuous at a left endpoint A or a continuous at right point endpoint B of its domain if the limit as x approaches A from the right, so we're going to the left endpoint of f of x equals f of A. Respectively on the going to the right, the limit of f of x as x approaches B from the left, so we're moving from the left, moving towards the right, as long as it's the same as f of B. Continuity at a point. continuity of point. If a function f is not continuous at a point C, we say that f is discontinuous at C, and C is a point of discontinuity of f. Note that C need not be in the domain of f. So one of the things to keep in mind on this one here is that, especially piecewise functions, you may find things that are not working. They're not going to be continuous, but we do have to watch for things. So let's look at the type of continuity. The typical continuity types are, so this one is, there's no discontinuity here. Basically, the function they gave you here is y equals x plus 1. There's no breaks, no nothing here. And then you have this guy here, which you barely can see, has an open circle there at 1. So this could be the function f of x equals, I don't need that, f of x equals x squared minus 1 over x minus 1. I put in 0, I'm going to get, well, I guess this function wouldn't work because if I put in 0, I'm going to get 1. Oh, I get 1. But it does have a discontinuity, you know, this just isn't working. Maybe it's x squared over x. X over x squared? Never mind. This one would be a removable one, so this one this is where it would look like a piecewise function, because you have an open circle here, but you have a closed circle here. So you would get, you know, x plus 1 as long as x does not equal 0. And you would get 2 when x equals 0. So I've got the wrong function on this one. It's driving me crazy now because I want to fix it. So this one, so those are both considered removable. So somehow you can get rid of a function in the bottom and you're left with this. And then we have this one here. This was a jump. This could be your absolute value of x over x or anything like that. If this one was that, you would have the open circle going this direction as well. This is an open circle, but this is what they mean by jump, that at that same point, one jumps to the other side. This one, they gave you the function. This is infinite because both sides go off to positive or negative infinity. So it's an infinite one. And then we have an oscillating one where it goes through and it just kind of bounces up and down until it gets close to that number and then jumps it and then does it again. So this is an oscillating one. You can see this is y equals sine of 1 over x. And it's just the idea of what happens on these as they go through. Most common ones you're going to see is going to be the removable, these two here, and these two here. Oscillating one you're going to find mostly when you're doing trig. So on this one, find and identify the points of discontinuity of this guy. Well, to find the point of discontinuity, we would do x minus 1 equals 0. So x equals 1. So our vertical asymptote is at x equals 1. I can draw it in there easily. Now, find and identify the points of discontinuity. And what's the type of discontinuity? The type would be infinite, because both sides are going off to infinity. So, but our point of discontinuity is at x equals 1. Okay, try another one. This one here don't really have the graph to look at, but if you still grab the denominator, x equals 0. So that is going to be our point of discontinuity. But what is the type of discontinuity here? Now, if you can always graph it, that's one of your choices. But I'll let you know that you're going to have an open circle here that going this way, and an open circle here going this way. It's jumps at the same spot. So this one is a jump, discontinuity. Some of them you're going to be able to identify really easy, others not so much so. Okay, a function is continuous on an interval if and only if it is continuous at every point of the interval. A continuous function is one that is continuous at every point of its domain. A continuous function need not be continuous on every interval. Now, this is where I am going to kind of point out the one we did earlier, where we had the square root of, it was 2x plus 3. And we had the domain came out to be negative 3/2 to infinity. This is what they're referring to. A continuous function is one that is continuous at every point of its domain. There's its domain. This guy is a continuous function. There's its domain. There are no jumps in the domain. A continuous function need not be continuous on every interval. It's not continuous where it's not defined. So we had done that. So when they say continuous function, you find the interval, basically you're identifying its domain, and anything else is going to be where it's not continuous, obviously, but it's because they're not part of the domain. So this one here, the given function is a continuous function because it is continuous at every point of its domain. It does, however, have a point of discontinuity at x equals -2 because it's simply not defined at -2. So here's a couple of questions to ask. Let's look at this. If I asked you, is it continuous on the interval of -5 to -3? And you'd be going, well, 1, 2, here's 3, and over here's 5. Yes, it's continuous. So you're going, yes. And then I go, well, what about 3 to 5? And again, you do 1, 2, yeah, you're way over here, and I know it looks like there's nothing more attached there, but these numbers are so close to 0 that it just doesn't show on the graph. But you still go, yes, yes it is. But what if I say, how about -3 to 3? Now I'm looking from here to here. But it jumps the point of discontinuity here. So the answer is no. It's not continuous on the entire interval. Therefore, this guy right here is where it loses because it's discontinuous at x equals -2. And x equals -2 is in this interval, therefore it's not continuous. Okay, properties of continuous functions. If a function f and g are continuous at x equals c, then the following combinations are continuous as well. Sums. If f is continuous, g is continuous, then f plus g is continuous. Differences. If f is continuous, g is continuous, then f minus g is continuous. Same thing with multiples. If f is continuous, g is continuous, and I multiply them together, then f times g is continuous. Constant, k times f, for any number k, f is continuous, I multiply it by 2, guess what? 2 times whatever f of x was is still continuous. And then your quotients, f over g, as long as g of c does not equal 0. So you have 1 over x, not continuous at 0. But any other interval, it would be continuous. So do be careful on, as long as we're talking about the domain, we're good, because as we move into calculus further, we will break it down. I will give you an equation, and I'll say, okay, we're looking at the interval of 3 to 5. I don't care if it's not continuous everywhere. I just care, is it continuous at between 3 and 5? Okay, composite of continuous functions. If f is continuous at c and g is continuous at c, then the composite g of f is continuous at c. So let's come with a function. F of x is equal to the square root of x plus 2. And g of x is equal to x squared plus 3. I'm going to identify the domains right away. The domain on this guy is going to be x is greater than or equal to -2, or -2 to infinity. This guy is all real numbers, interval notation, -infinity to infinity. When you do the domain of a composite, the domain of the, well, first of all, let's do g of f. G of f of x is equal to x squared plus 3. But I'm putting f of x in here, so I'm going to put x square root of x plus 2 here. This gives me x plus 2 plus 3, which leads me to have x plus 5. Now you can't claim the domain to be all real numbers. Your domain, now keep in mind that it says that if f is continuous at c and g is continuous at f of c. So at this one here, our domain is now going to be the intersection of f of x intersected with g of f of x. So, and this is what they mean by g is continuous at f of c. You know, whatever the c value is. So f of x is from -2 to infinity, and g of x is all real numbers. So this guy, even though you're going, but it looks good, you're only allowed to use these values, because that's the domain of it. Now we can go the other way, because they can claim this as well, that g is continuous at c and f is continuous at g of c, then f of g is continuous at c. So let's look at this the other way. What if I did f of g of x? Well, now I have the square root of x plus 2, and that's going to be x squared plus 3, which is going to give me x squared plus 5, and the domain is going to be g of x intersected with f of g of x. Now, g of x is all real numbers. And this guy, as long as he doesn't go negative, is fine. Well, I have x squared, which will always be positive, and I'm adding it to another positive number, so their domain as well is -infinity to infinity. So this one has a domain of -infinity to infinity. So you can see that you can get different domains out of each of these. This one here is f of x intersected with g of f, because now the thing to keep in mind here is, especially this one, is that I took the x out. That's why I lose the domain for the f of x. I took x out and put g in. That's why I keep the domain for g. And then I have my new equation, and I grab that one as the intersection of. Same with this one here. I did g of f. I'm keeping f. I'm placing it inside here, so my domain for f cannot change. But g's domain goes away because I have a new function. It just didn't make a difference. Still got the same domain. Okay, video is going a little bit longer than I wanted to, but we are almost done. Intermediate value theorem for continuous functions. A function y equals f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in a to b. They're just saying, hey, if I've got this line here, and here is f of a, and here is f of b, then some point here is going to be f of c, because it's a continuous function. That means I need to be able to draw a line through all of them. The intermediate value theorem for continuous functions is the reason why the graph of a function continuous on an interval cannot have any breaks The graph will be connected, a single unbroken curve. It will not have jumps or separate branches. Okay, this is the end of section 2.3. Like I said, it was running a little longer than I was hoping, but I hope this helps you guys out.